All right, this is our first video on energy, just about the basics, a little intro. We're just going to talk about the definitions of some of these guys, and then what's on page 2, the mathematical expressions for the most important types of energy, really the only types of energy that we're going to be dealing with. So, at least for now. So, first we'll start just with some of our important vocabulary. We had some definitions already in class, ideas about how we could define energy. Lots of different definitions we could use. We're going to use the capacity to do work. Because we need something that involves work. Energy and work are inherently connected. They can't be divorced from one another. They're like, for lack of a better phrase, two sides of the same coin. And if we look at my definition of work, we can see how they're related. Forces do work on objects or systems. That's important to remember. Work changes the energy of an object or system. And work done by a force is essentially the force multiplied by how far the object moves in the direction of the force. So one way to think about force is just work is force times distance, though that's not really specific or accurate enough for us to use, but it's a good thing to remember. It's essentially force times distance, where distance is the distance over which the force is being applied, if it's pushing or pulling on an object. So force times distance, that's what we mean by work, and work changes the energy of an object or a system. And a system is just a collection of objects. So energy is the capacity to do work. If you have energy, then you can do work. You can exert a force over a distance, essentially. And if you do work on something, and anytime we're talking about work, we ask work done by what? By what force? Acting on what? On what object or system? And if you do work, then you can change the energy of an object. So good example from the last lab, the first lab we did, you release the Hot Wheels car. Gravity does work on it to make it speed up. Gravity does work, so it changes the energy of that Hot Wheels car. It makes it speed up, so it's increasing its moving energy, or it's increasing its kinetic energy. Skip the next two for a second. Kinetic energy, energy of motion. Potential energy is you can think of it as stored energy, but sometimes it's better not to think of it as stored energy, but to something else. We'll get to that when we get to that. But potential energy is essentially the energy an object possesses or a system possesses based on its position in relation to other stuff. So like where the Hot Wheels car is in relation to the Earth determines how much gravitational potential energy it has. So that's the next definition, the potential energy possessed by an object due to its position in a gravitational field. So gravity is an attractive force. It's pulling the Hot Wheels cart towards the center of the Earth. So if you lift up the Hot Wheels cart higher and higher, you're lifting it up in the opposite direction as the gravitational force is trying to pull it down. And as you lift it up higher and higher, it's kind of like you can imagine it's like stretching out a rubber band. You're creating more potential energy by doing work on this Hot Wheels car, lifting it up higher and higher. So as you separate the distance, make the distance between the Hot Wheels car and the Earth larger, it's like you're stretching out a rubber band, you're increasing the gravitational potential energy. Spring potential energy is similar. It's like energy you can store in a spring or an elastic band. You stretch it out or expand it. You have energy that's stored in there. If you let go of it, it's going to snap back. You'll have kinetic energy that's being transformed after you let go of it. Or you could compress a spring. And the spring constant K is used in defining exactly how much spring potential energy there is, and also defining what the spring force is for a certain spring. The spring constant K is just usually a generic term for any constant. So in the context of spring force or spring energy, K stands for the strength of the spring, or the spring constant. A big value for K means it's a stronger spring. A stronger spring means it's harder for you to compress it or stretch it because it takes more force to do so because it's a stronger spring. Mechanical energy is the last important one we'll define in yellow here of the basics. The mechanical energy is simply the sum of all potential and kinetic energy in a system. Of these particular forms of energy that we're talking about, mechanical is everything. All kinetic and all potentials. And so there's our kinetic, our symbol. Here's how we express it mathematically. Make sure you're familiar with that. Potential energies, these are the potential energies we're dealing with in this unit. UG is mgh. That's our gravitational potential energy. US is 1/2 kx squared. That's our spring potential energy. You can see all those terms and symbols are defined there for you in those equations. So read through that. Up here at the top, we will mention sometimes mechanical energy is symbolized with ME or TME for total mechanical energy. Okay, we're just using capital E. We don't get time for that TME stuff. Just capital E will represent all mechanical energy. All energy, all forms of energy are measured in joules after James Prescott Joule, who did lots of stuff. Among other things with like heat engines and efficiency with machines, some really neat stuff that involved energy. Okay, so he's got kind of like the Newton, he has his own unit named after him. 1 joule is equal to 1 Newton times 1 meter, which can be written as 1, capital J is the abbreviation for the joule, equals 1 Newton times meter. 1 Newton is 1 kilogram meter per second squared, because Newtons are mass times acceleration. So 1 Newton is 1 kilogram meters per second squared. So that means also by substitution, 1 joule is going to be 1 kilogram meter squared over seconds squared. So that's in base units what the joule is equal to. You should be able to figure that out just because you should know what the Newton is because it's forces mass times acceleration, MA. Know the base units. Energy is a scalar quantity, so meaning it just has magnitude only or amount only, but not direction. You can have positive and negative energies. You can sometimes use, and we will use, positive and negative values to indicate an increase in energy. A positive value if an object gains kinetic energy, you might say it's changing kinetic energy, is positive, and you'd have a positive number of joules. Or if it lost kinetic energy, it slows down, for instance. You could say its change in kinetic energy is negative because it lost energy. So pluses and minuses can be used here to indicate an increase of energy or a loss of energy, change in energy. But the energy itself does not have a direction. So the pluses and minuses are not indicating a direction. That being said, last thing that I want to say are the terms that may be the most difficult to define, but they're clear in practice. So once we especially start doing LOL diagrams, we'll be good with the system and the environment. The system is a collection of objects. When we diagram a system, we're going to have a circle. The circle is going to represent the system boundary. And the system, like you could think about your body, your human body is a system. It's a collection of other systems too, actually, right? You have a respiratory system, a circulatory system, etc. So you could say like, well, my skin is like the system boundary between my body and the environment. Everything outside of this circle or outside of the system is the environment. And the environment's filled with literally everything else in the universe. And within my system boundary are the objects that make up my system. My system. Okay. And that's like almost all I want to say is just about like system and environment. Environment is everything else. System is like the stuff you care about when you're examining what's going on. Because really everything's connected, right? Everything's affecting everything else, but we can focus on just the Hot Wheels car. For instance, we could say, okay, my entire system is just the Hot Wheels car. There are forces acting on it. Those forces are doing work. Those forces that are doing work are changing the energy of my Hot Wheels car. And as time goes on, well, what happened, it increased its kinetic energy because the network was being done. The total work was a positive amount of work done by gravity, which resulted in a speeding up of my Hot Wheels car. And I'd be clear about saying, okay, if the Hot Wheels car is the only thing in my system that I want to talk about, then I would put my Hot Wheels car as the object inside my system boundary. And if I wanted to describe the gravitational potential energy of that Hot Wheels car, I would need to have the Earth as part of my system and name the Earth as an object within my system boundary, because you can't have gravitational potential energy if you don't have the source of the gravitational force. Okay, so we will come back to those and draw them quite a bit. I can have a system, and the environment is just everything else outside, and I can sometimes have my system do work on the environment, which we draw arrows to show coming out. So sometimes the system can do work on the environment, like friction. If I slide an object down a ramp and there's friction present, it could heat up the ramp. The ramp is part of the environment a lot of the time if you examine just what's happening to something sliding down a ramp. So the ramp's part of the environment, and your system could do work on the environment, could do work on the ramp by heating it up, because the friction is going to give it some dissipated energy. So in the form of heat or thermal energy, it makes it warm up. So work on the environment or energy leaving the system we call dissipated energy, or EDIS. That's dissipated energy. It's leaving the system. EDIS, or dissipated energy, and that's frequently in the form of thermal energy from friction, frequently. Okay, or you could have the environment. The environment could do work on the system. Okay, so you run up out of nowhere and give the Hot Wheels cart a little push, like you're adding energy to the system, you're doing work on the system, and this is the way that we'll think about our objects in our system. System is everything inside of our boundary, inside of our circle here. We list those objects. Work can be done on the system, or the system can do work on the environment. The environment is literally everything outside of the system. That's it for our initial definitions. And yeah, that's it.